We're in the middle of this massive energy revolution, right? We're shifting our power grids to cleaner, greener sources like wind and solar. But there's a catch. This transition comes with a hidden challenge. As we add more of these incredible new technologies, the very fabric of our electrical grid, well, it gets a lot harder to predict and control. So in this explainer, we're going to dive into these invisible complexities and find out what it really takes to keep the lights on.
First up, the grid's unseen dangers. See, the stability we all just take for granted with our power supply, it isn't guaranteed. As we move away from those big, old-school power plants, we're uncovering new, invisible dangers that threaten the reliability of the entire system.
So what is this hidden weakness? Well, it's actually in the very tools we use to see and predict how the grid is going to behave. For decades, our methods worked just fine. But with the rise of renewables, they're starting to show some pretty critical blind spots.
And look, this isn't just a theoretical problem. We got a huge, real-world wake-up call back in August 2019. There was a disturbance in the UK grid, and it caused a whole bunch of generation, including wind farms, to just unexpectedly trip offline. Why? It happened because the models they were using to predict their behavior during a fault just weren't accurate enough. It revealed this massive gap between our simulations and what happens in reality. Okay, this brings us to the core of the problem. To understand our grid, we build these computer simulations, right? We call them models. And it turns out there are two fundamentally different ways to do this. And each one has its own very different strengths and weaknesses. The statistician George Box famously said, "All models are wrong, but some are useful." This is the perfect way to think about our discussion. We're not looking for a perfect model, because honestly, one doesn't exist. We're looking for the most useful model for the complex, fast-changing grid we have today.
So what exactly is a power system model? The easiest way to think about it is as a digital twin of the electrical grid. Engineers use it to run thousands of what-if scenarios. Like what if lightning strikes a line, or a big power plant suddenly shuts down. They do this to make sure the real grid can handle pretty much anything without collapsing.
Okay, so let's meet our two main characters in the story. On one side, we've got RMS, who we can call the veteran. It's fast, it's efficient, because it basically averages out the three phases of AC power into one and takes snapshots every 10 milliseconds or so. Then on the other side, we have EMT, the specialist. It's incredibly detailed, modeling each electrical phase all on its own and taking snapshots in microseconds. Totally different beasts.
So let's stick with that. Think of the traditional RMS model, like a blurry photo. It gives you a great sense of the overall scene, the big, slow-moving trends in the power system. For a grid that was dominated by giant spinning generators, this was usually good enough. But it completely, totally misses the split-second details. An EMT model, though, is the exact opposite. It's like a super high-resolution, slow-motion video. It captures every tiny, high-frequency wobble and flash, the exact kind of super-fast behavior that modern inverter-based renewables like solar and wind bring to the grid. So you might be thinking, well, if EMT models are so much more accurate, why haven't we been using them all along? That is a great question. And the answer is that all that incredible precision comes at a very, very steep price, creating some major headaches for grid operators and developers. This table really lays out the trade-offs perfectly. EMT modeling needs incredibly detailed data that can be really hard to get. A single simulation can take hours, compared to just minutes for RMS. The complexity is also off the charts. It requires some serious expertise, not just to build the model, but to make sure you don't get results that are just plain wrong. So yeah, at the end of the day, implementing EMT is a massive operational hurdle. You need more data, way more time, and a ton more expertise. Plus, the software just isn't always built to run the thousands of automated scenarios that grid planners rely on, which makes the whole process way more manual and really challenging. But here's the thing. Despite all those challenges, the industry is at a real tipping point. The very nature of a greener grid is forcing our hand, pushing us towards this more complex, more powerful way of seeing electricity. And this is why this all matters so much. The fast-acting electronics inside solar, wind, and battery systems, we call them inverter-based resources, they create the exact kind of fast, unbalanced split-second events that the old RMS models just can't see. So as these resources become the majority of our power generation, using the specialist EMT model is It's no longer a choice. It is absolutely essential.
Because of this, grid operators are creating a whole new mandate. Before a new renewable project can even think about connecting to the grid, its EMT model has to go through this really rigorous four-step process. First, the developer provides a super detailed model. Then, the operator verifies it's consistent. Third, and this is crucial, they validate its simulation results against real-world tests on site. And only then, finally, is it integrated into the main grid model.
And I want to be really clear, this isn't some far-off theoretical idea. This is happening right now. Grid operators in forward-thinking places like the UK and Australia are already making these validated EMT models a mandatory requirement for any new renewable project that wants to connect to their systems. And the resources required to do this are, well, they're significant. In France, for instance, the validation process for new connections required the equivalent of 1 to 2 full-time engineers working year-round. That just highlights how intense this new requirement is for both the grid operator and the people building the projects. And this all brings us to our final big question. We are racing to build a carbon-free grid, which is amazing, but the tools and the skills we need to manage it safely are incredibly complex. As the pace of building renewables outpaces how fast we can develop software and train skilled engineers, we have to stop and ask, is our technical expertise actually growing as fast as our green ambitions?